making it hard on yourself. So here's the question. Here's why I chose this. Does this look familiar right there?
I think it's a formula.
There's something for this, yeah. So let's think about some of the things. Like if I wrote it like this. Would that look more familiar? This is one of those things that you want to remember for the rest of your life. And when you see this, you should immediately think, you know what? This looks familiar.
Yeah.
And so then what should this be over here? Should be, which one was it?
It was plus or minus.
Yeah, but which function was this here? There's two possibilities for what this guy was. Remember, because the other one was right. And one of these was, one of them sine and one of them's cosine. Which one's which? Just take a guess. The top one is
Sine.
the top one is sine. And then the sine a plus or minus b, and the other one was cosine a plus or minus b. And so the reason I could have written this as this equals 2 sine x cosine x. I wrote it like that to kind of try to get you to remember, oh yeah, this is a thing. And so, like, oftentimes you'll have to do something. It might not be graph, it might be something else with it. But when you see this, this should immediately trigger in your mind, ooh, wait a minute, this is one of these types of things. And so recalling that, that means that this can be rewritten as what? What's the very simple way of writing this?
Sine of 2x.
Sine of 2x, or sine of x plus x, which works out to be sine of 2x. Now that should be easy to graph. In fact, I'm going to do it right now. Just jump to the chase here. We're going from 0 to 2 pi. And so, okay, here's x. I know sine starts here, comes up. That's one sine, but now two of them means that we're putting twice as many bumps in the same amount of space. So if that's 2 pi, then that's 1 pi. That would be half of pi. That would be a quarter pi. And then from there, that's a 1. That's a negative 1. From there I'm going to count 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters. I'm just going to go ahead and write it as 6 quarters, 7 quarters. And there you go. Now we've done what we're supposed to do. I was saying to Noah, I'm going to try, I've said this before, I'm going to try, now that we're getting out of trig, I want to try to do a problem of the day every day where we just do some kind of refresher like this. Because you're totally going to see that. Well, you're going to see this stuff for the rest of your life. And every now and then something like that's going to pop up and you're going to go, and it might not be graph it might be a bunch of different things with it. And if you could recognize, oh wait a minute, there's an identity for that. That's the same thing as this. Writing it like this may or may not make your life 10 times easier. Especially in calculus, when we have to integrate something like this. We can get into what an integral is when we do calculus, but trying to do it with this in there is going to be very hard, I think. Yeah, you'd probably do it like that. Still difficult, but if you do that, it's very easy, like so easy. And so, and graphing too. You can imagine if you tried to graph that by plugging in pi, really? I mean, you could. And you plug in pi and you'd get a 0.
Oh.
Right? Because you'd have f of pi is sine pi, which is 0, and so all the other stuff, and then sine again, pi is 0, and so you'd say, okay, 0. And so now you go
to its also.
and now you have 1 point, and there's your graph. And you'd have to plug in about infinitely many more to get all of the other points and blah, blah, blah. But yeah, the whole point of this exercise was that we don't forget these nifty identities, especially the sum or the, I don't know if we have a special name for those, but those guys. Those are really, really important. The sum of the inputs goes to a sum of the outputs. That's really, really, really useful. So, okay, here we are. We're moving on. We are now in chapter 10, and you can see, this is your homework, right? Page 745, 1 through 27 odd. So, this section is called infinite sequences and summation notation. We're doing infinite sequences today. And infinite sequences are usually denoted like this. A1, A2, A3, and they go on forever. And in general, we have AN, and so on, and they just go on forever. And these are just numbers. They're real numbers. Okay? It could be any numbers in the world. They don't have to be in order. Right, I could just make one up. I could say, okay, here's 35, root 2, 7 over 101, e to the pi, and so on and so forth. And I could just go on for infinity, right? And that it technically is an infinite sequence because it's an infinite sequence of numbers. It goes on forever and ever. We usually use A to denote these. That's pretty standard. Okay, each one of these things, and we'll just say A sub k, this is called a term of the sequence. And the one with subscript k is in particular called the kth term, right? A sub 1 is the first term. A sub n, you're going to hear this a lot, is the nth term of the sequence. That's what we're talking about. So if I said the 45th term of the sequence, it would be the 45th one, and we would write it as A with a little subscript 45 right there. Everybody got that? Yeah. Okay. They're often defined by giving a formula for the nth term. We're going to do that in just a minute. In fact, a lot of what we do today will deal with that. But we'll go into that in just a second. There's other ways of defining them, and like I said, I could just write down a string of numbers, and that would be a perfectly good infinite sequence. So here's an example. 1, 1.4, 1.41, 1.414, 1.4142, and so on. Square root of 2. Yeah. And this is what your book says. Well, it doesn't use this one, but it says that this sequence, the entire thing, can be used to represent the number square root of 2. Now, here's the thing. This is an aside. We are not doing this in this class. We're not going to worry about the stuff that I'm about to talk about. But since the book made a statement like that, I have to go into this because it also ties into something I said last year. So, now, in this case, the nth term, right, we're saying like after you get to a to the n, the nth term gets closer and closer to the square root of 2 as n goes to infinity. We could write that as the limit as n goes to infinity of this sequence, meaning that this number, this number gets closer and closer to square root of 2. We'd say that the limit equals square root of 2. Now, in calculus, and especially if you go beyond calculus and do analysis, this type of thing, finding out the limit of a sequence, or whether a sequence converges to a specific number, is one of the central things you talk about. we're not going to do that. But check this. This is... So, the book says that this sequence itself can be used to represent this number. Or how does it put it? It can be used to represent this number. And ditto for other sequences too, right? Here's a sequence. How about, which ones did I want to use? I didn't want to do that one yet. We'll do it anyway. Here's 1, 2, 3 halves, 4 thirds, 5 fourths, how about 6 fifths, and so on and so on. This is converging to a number. Can you guess what number it's converging to? It's getting closer and closer to a specific value. If you think about it.
Wait, 33, yeah.
Well, let's think about this. This is getting bigger, and so like for instance, when this is 10, this would be 9. When this is 100, this would be 99. When this is 1,000, this would be 999. It's getting, this sequence converges to the number 1. But there are other sequences that converge to 1 too. So like, how about this one? How about 0.9, 0.99, 0.999, and so on and so forth. Right? That also converges to 1. Let's be a little bit trickier. How about 2, 0? How about 1.5? How about 0.5? How about 1.25? How about 0.75? You see what's happening? I'm bouncing back and forth. Like if we were to think about it this way, I'm starting up at 2, then I'm going down to 0. Then I'm coming up halfway between, then I'm going down halfway between. We're bouncing back and forth, but guess what this sequence is converging to? It's still converging to 1. And so this is the thing. I have to talk about this. Indeed, so last year I said these sequences, or I didn't say this, like we were going to talk about sequences, but last year we talked about the real number system. And I said that real numbers are, we didn't define them in class. We didn't go like formally, but we defined the natural numbers, which were, and this was in that first handout I gave you guys. The natural numbers were 0, 1, 2, and so on. Then from there we said, well then, we're going to define the integers, which are all of these and their negatives. So you get all of these guys and all of their negatives. From those, we can get the rational numbers, which are just ratios of these guys, right? A over B, where each A and B's are just integers, right?
Yep.
So like 745ths is indeed is a rational number because both 700 and 45 are blah, 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 blah. Then I said real numbers are something else. And I said the way they're defined is just so ridiculous that it's basically laughable, and I didn't tell you how they're defined. Well, this is how they're defined. You take the entire set of infinite sequences. You imagine all the infinite sequences. Like, here's one we've seen before. 0, 1, 1, 2, 3, 5.
It's an infinite sequence of infinite sequences.
Well, we're not putting them in sequence. We're just saying take all the infinite sequences. Okay, here's one. And remember this one? This is the Fibonacci one, right? You add those two together to get that one. Add those two together to get that one. Add those two together to get that one. Add those two, blah, blah. But you can see that this doesn't converge, right? This is going to go off to infinity. Okay, so you take all the infinite sequences, and then the ones that don't converge, like this one, here's another one that doesn't converge. -1, 1. -1, 1. -1, 1. It bounces back and forth between -1 and 1, and it doesn't ever converge. It doesn't ever settle down on one number. So you take all the ones that don't converge and you throw them out. Now what you do is you take the remaining ones, all the ones that do converge to a number. And what you do is you define, you say, well, every infinite sequence that converges, and this is, since we've now defined what these are, we're taking infinite sequences of rational numbers, which each one of these are sequences of rational numbers. They all converge to the same number, which is 1. And so then in the real numbers, we say that the number 1 is then the set of all sequences that converge to 1. Yeah, that's how the real numbers are defined. That's how they're defined. The real number 1 is the set of all rational sequences that converge to 1. So what is 1? Well, it's that sequence, and that sequence, and that sequence. All of them together is that number.
But
There's infinitely many of them. So every one real number is an infinite set of infinite sequences. Yeah, and yeah, it's very shaky ground, really. I mean, it works, though. And all of the properties that you want with real numbers, like you give me any two real numbers, here's one property that you want. You give me any two real numbers, and they have the following property. Either x is less than y is less than x, or it's the case that x is equal to y. Well, you start with this definition, and you could show that this is true. And all of the other things that you want from real numbers, not just this property, but all the properties of real numbers that you want, you could show that by defining them this way, that the number 1 is all of the sequences that converge to 1. It actually works, and that's how they do it. There are other ways of doing it, but formally, if you take a class in analysis, this is how it will be defined. And then you're going to just go to town on sequences. And then, yeah. Anyway, I had to say it, because last year I was like, you don't even want to know how they define real numbers. We'll just say that they exist. This is how they're defined in terms of infinite sequences. So that is an aside. You do not need to know about convergence. I'm not gonna give you a sequence and say, what does this converge to? That's a calculus problem. That's an analysis problem. We will sometimes
we did that last year, right? Like with the root 6. It was similar.
It's similar. And we will be just in this section we will be talking kind of about that. But I'm not gonna give you a sequence and ask you what does this converge to. Actually, I might. I mean, if it's obvious, something like 0.9, 0.99, 0.999. But that's not really the point of all this. This is just to introduce infinite sequences. And so here's a definition. Here we go. So now you need to put your listening ears back on, and we're going to, now all this stuff you're responsible for. An infinite sequence. An infinite sequence is a function, whose domain is the set of positive integers. And in our book uses the strictly positive integers, 1, 2, 3, and so on. Our book does not use 0. Plenty of authors will use 0. So the authors that do will say that every infinite sequence looks like this. There is a 0 term. Our book doesn't, and that's what we're going to roll with. And it does not matter. It's the same stuff. Okay? It's really the same thing. It's just our book had just had to make a decision and said, we're going to leave off 0. We're just going to say they all start where the inputs are 1. And so what does this mean? So let's think about this. We had a sequence earlier. It was this: 3 halves, 4 thirds, 5 fourths, 6 fifths, and so on. And one thing, what we called it, well, what we have up here is we could say this is the same thing as our A1. This is the same thing as our A2. This is the same thing as our A3. This is the same thing as our A4. This is the same thing as our A5, and so on and so on. And finally we get up to AN. Okay, we'll do that in a second. But it's not so much that it's this actual string of numbers, although this is exactly how you're going to think about a sequence. Whenever you think of a sequence, when I say sequence, and by the way, I'm just going to say sequence, and in our class we're going to take that to be infinite sequence. So I don't have to say an extra 3 syllables every time, right? So when you think sequence, you should think of a string of numbers like that, but what it is, the definition, is that it's this function which, when you plug in a 1, it gives you a 2. When you plug in a 2, it gives you a, in this case, a 3/2. When you plug in a 3, and so you kind of see what's happening here, right? Instead of saying that our general sequence, our general infinite sequence is a string of numbers that's like this, it's just a little bit easier. Like we could do that. We could have, like, I could have written that up on the board. Nobody does that because it's so much easier to just say A1, A2, A3. But every one of these things that we have, every one of these A's, it is, you could think about it as a function. And so you could think about this A4, yes, it is what you get out when you plug in a 4 into the function. But this like little 4 here is almost like an input. Okay, so that each one of these subscripts is like an input to your function. Okay? Questions on that? It's a little, I mean, it may be a little funky, it may be obvious, you know. So, okay. So again, you can think about these, and this is also called the index down here. Each one of these is called the index. And so you could think of these indices as the inputs. Now, in general, we don't even write it as f of something. So when I want to describe a function, a general sequence, if you're given a formula, usually write it like this. So instead of writing your f of n, you have your a sub n. And so when you see that, some function of n, like, I mean, I could have written this right here, some function of n. But we're going to switch gears right now and change notation and say, instead of this thing, f of n, this is the exact same thing, but this is how we're going to write it. There's some formula whose input is n, and when you see that, you know, okay, this is what they're talking about then. This is the thing that this is. In fact, I'm going to go ahead and do that and say this string, infinitely many numbers, it goes on forever, is represented with a little set brackets with an a sub n in there, or a b sub n, or any letter sub n. That's what we're talking about. Okay? That's something I didn't write down in my notes. Two sequences are equal if and only if every one of their things is exactly equal. Okay? So it's just, your book says that, and I didn't bother to write it in there.
On the, like,
So-
if it's the same thing.
If it's the exact same thing, right? That's why I didn't bother to say it. But it's good to know, because you might say, well, hold up, that converges to 1. So does this converge to 1. Are they the same sequence? Technically, no. They're different, because each one of them aren't exactly the same. Yes, they go to the same place. And yes, if you're talking about a real number, they're in the same group to define that real number, but ugh, what a pain, right? So just the only way that two sequences, and since it's a function, this kind of makes sense, because if you remember before, we have this thing. We'll say if this is a function f of x, and if this is a function g of x, I was going to say f of g, g of x, yes, they might be the same here and here and here and here, but are they the same function? No, they have to agree at every single point. And so it kind of comes from this fact right here that we're defining them as, that this thing is a function. For the two to be equal, well, they have to have the exact same output every time you have an input. And so they have to agree at every single one of these, because each one of these, this just means the thing you get out when you plug in a 1, the thing you get out when you plug in a 2, this is the thing you get out when you plug in a 3, and so on and so forth. So that just like functions, if they're the same thing, they have to agree at every single point. And so that's what that means. I didn't bother to write it down. I don't know if it's going to show up later. I don't think it is, but it's good to know. So, okay. So finally, now let's get into the bread and butter of like what we're doing here. Everybody got this? Can I erase this stuff?
Yeah.
All right, so let me give you a sequence. Here's a sequence, and I'm defining it by the nth term here. This is your a sub n is that thing right there. A sub n is n plus 1 over n.
It's the same sequence.
And so what number do we start with n?
1.
1.
Would be.
Well, yeah, the first input that we throw in is a 1, which gives us a 1 plus 1 is 2 over 1, which is that. And then what's the next one?
3 halves.
Right. And the next one?
4 thirds.
4 thirds. And what's the nth one? Well, that's the nth one, right? N plus 1 over n, and so on and so forth forever, right?
Or
Okay?
it could be n over n minus.
You could, yeah, here's the thing. I wasn't going to get into this. So here's the thing, right? So like, if we had this,
Then it would start with 2.
could we, yeah, you couldn't
Yeah,
start at
we'd start at
1,
this.
right? And so it's like, if you had that, you'd have to either specify that n starts at 2, 3, and so on, and then say, okay, well, if n starts at 2, then you have a 2 over 1, and lo and behold, they're the exact same sequence. Or you'd have to do some other stuff, right? Or, and so your book is not going to give you any tricks like this. It's going to assume that every single time you're plugging in a 1 first, okay? And so on and so forth. And again, other books will allow 0 to be the case. And so if you could plug in a 0, you'd see, well, that doesn't work. And so you'd have to do the other thing. You'd have to go n plus 1 over n plus 2 to get that, if you were indeed starting where n equals 0,
Yeah,
1,
okay.
2, and so forth. And then you'd say, okay, if I plug in a 0, I get a 2, 2, and a 1. Plug in a 1, I get a 3, and a 1 gives me 2, and so forth. And you could see that, yes, they're the same sequence, right? So, depending on where you start, your book is always going to start with 1, because of the way they define this thing. But not every book is going to do that. Okay, now, here's the question. Find, all right, we already did it. I meant to write that up there first. We're given this. We're going to find the first 4 terms and the 10th term. So we have the 1, 2, 3. What's the 4th term?
5 fourths.
5 fourths.
11.
And then there you go, right? Because you could just say, well, the 10th term is the one with a 10. And then you just, that's the input you're plugging into that function. And so that's 10 plus 1 over 10, which is 11 over 10. Okay? And graph it. Okay, so here's the thing. Now, I do want to do this. First off, let's pretend, before we do any of this, let's just pretend that I gave you a function f of x, and it were x plus 1 over x, and I told you to graph that. Now, you might hate me for that, and go, we never talked about doing that. I don't know how to do that. And so then you just start playing with this, and you go, well, this is the same thing as this, right? Is that the same thing as that?
Yeah.
Yeah. And so is this the same thing?
Yeah.
Yeah, and you know how to graph this part, right?
Yeah.
That's 1 over x. That's just, you know,
Sure.
it just goes down like that and goes like that. And now we're shifting it what?
Up 1.
Up 1. And so instead of this being the asymptote, this guy right here would be the asymptote. And so he comes down like that, and he comes down like that. And that's what you would do if it were a continuous function. This is not a continuous function. It's not defined on all of the values, right? The only values we could plug in here are 1, 2, 3, 4, and so on, and 5. And so the only outputs we should get would be 2 and 3 halves, and so on and so forth. And so if I were to graph this, I wouldn't put any of this stuff in there. I wouldn't put that there. Your graph should just be dots. And that's all it is. There's no, and there's really no difference. It's like this is like a special case of the continuous case where you're allowing all real value inputs. Well, all of them except for 0, but, right? So this is what your graph would look like for a sequence. It's just dots because you have one input, one output. One input, one output, one input, one output, and it's just dots. Does that make sense? Questions on that? Okay. Don't connect the dots. Like, that's not, because that's not the case. This sequence never takes on this value. This value halfway between here, which would be, oh no, what's something between 3/2 and 2? How about 7/4?
Yeah.
There you go. The output of this thing is never 7/4. There's never a 7/4 here. It completely misses it. Okay? So you can't connect these dots because it doesn't take on all of these values between. The only ones that it takes on are these ones right there. So that's what your stuff should look like. I'm not going to be too concerned about asymptotes, though, I mean, especially if I gave you something like this, you may or may not see that it is approaching 1. But now it's kind of easy to see that it is approaching 1, isn't it? Like coming from doing like this, what happens if you make x really, 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 really big? This gets really, 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 really small, and you're approaching 1 as you get closer and closer. And there are other sequences. And so like I said, the real number 1 is defined as all sequences which approach this line, basically. So if there's a sequence that does this, and gets closer and closer to 1, then that sequence is part of it. Or if it's something that starts here, or, well, I guess technically we have to start here. If it's something that does this, then that sequence also is part of number 1. Sorry, I will not talk about the definition of real numbers ever again. I hate the real number system. I don't believe it. I think it's a cop-out, but it is pretty cool what you could do with it. Okay, so questions about this? This is one of the homework type problems. Find the first 4 terms and the 10th term and graph it. But it's not all together. You have to graph in another part, but that's what we're going to play with right now. Okay? Okay. Okay. So again, I just want to say we are not concerned with convergence in this class. Even though you could see once you graph that it does converge to a value, we're not going to worry about that right now. But we're going to do the same thing, find the first 4 terms and graph it. Here's this. -1 to the n plus 1 times n plus 1 over n. What's the first term? Plug in a 1. What happens to this guy?
It's just -1.
-1 to the what?
Squared, so just 1.
Aha! And so that's just 1. And so then the first term, evaluating the rest of it, gives us what? 2 over 1, or 2. And I'll just write as 2 over 1. Okay, what's the next one?
So 2 with a -1 cubed, which is just -1.
-1.
And then
Times 3, which is -3.
So
over
negative.
2.
is over 3 is negative. Over 2.
Yeah.
Yeah, over 2.
Mhm. Now, when n is equal to 3, we have -1 to the what power?
4th,
Which
one.
is just 1.
5 over
It's what over what?
5.
4 over 3.
How about 4 over 3? Okay. And then can you tell me what sign do you think the next one's going to have?
Negative.
It's going to be negative. And this is why I chose this one, is because like this thing is so useful. So useful. I call it a blinker because it kind of blinks on and off, right? With every single term in the sequence. It's one's positive, one's negative, one's positive, one's negative. And
Don't have a 4 in the denominator.
and then how about, since that one was negative, the next one would be positive. And so, okay, now let's do the 10th one, right? Because that's what we're doing. That's what it says to do. Find the 10th one.
So
It's
negative
11 over.
what? Negative.
Is it negative or positive?
It's
So-
negative.
Okay, because and you plug in
Because
10 plus 1, that's an odd, which means negative, so we know it's negative. And then it's what over what?
11 over 10. Yeah.
11 over 10. There you go. Now we're graphing it. Okay, so this blinker, I call it a blinker. It's very useful. So, and before we graph it, for instance, find the formula for this sequence.
And
What's the formula for that?
And
Just plain old n, right? And it's obvious. If I gave you that, you'd say, well, it's just 1, 2, 3, 4. Now, what about this one?
oh, n to the 1 to the.
Yeah, so this is the thing, is like, whatever it is, you know that it's n, and now you
Oh.
need a blanker, so you're gonna plug in your blanker. Now the only question is it n or n plus 1? Where do we want it when n is
You want most positives on the odds. So it must
Positives
be
on
to
the-
be n.
so when n
Oh, I
is
see. Okay.
1, n is 1, making it negative, so we don't, and this is the great thing about this, it's so simple. If you get to this point and you go, uh-oh, when I plug in a 1, I get a negative 1, but it's supposed to be positive 1, just add 1, boom. Oh, that's it, right? Now if I asked you the other question, minus 1, 2, minus 3, 4, you'd say, well, it's something with n. It's a blanker, so it's a negative 1. Now, is it n or n plus 1? And let's say you guessed wrong and you said n plus 1. Now you just go to check it and say, well, when I plug in a 1, what do I get? I plug in a 1, I get a 1 here, so I'm good. I plug in a 1 here and I get negative 1 squared, gives me a positive. Uh-oh, we'll just take that guy off, right?
Yep.
That's the cool thing. The blinker is so useful, so useful. When you take calculus, it's so useful to be able to go, hey, wait, this thing's, and this is also, by the way, called an alternating series. This is an alternating series. This is because the sign alternates with each one. Anytime you see an alternating series, you know that one of these blinkers is there. You just have to figure out which one it is, and then when you go to check your work, if you got the wrong one, just add a 1 or subtract a 1. You know, it's quite easy. So it's just good stuff to know. Okay, so now we need a graph. So I'm going to graph this guy, and really, we know we're starting at 1. And, by the way, so we're going to go 1, 2, and we don't need to do. For your homework, I mean, you don't have to go all the way to the 10th term or anything. Just as long as you get the general idea of what's going on here. Right. Now, plug in a 1, we get out a 2. So I'll do my 2 up here. Now it's negative 3 halves. So negative 3 halves is this guy. 4/3 is for this one. So we'll do a 4/3 right there. This is what I expect, right? I don't, as long as generally these things are decreasing, as long as generally these things are increasing, your negatives are actually negative, right? That's what I'm looking for. I don't want you to measure anything, but just qualitatively accurate. The 4th one was a negative, and so negative, but not as negative. Negative 5/4 comes up. The 5th one would, we didn't do it, but it would be positive 6/5, and so positive 6/5 is right there, and so on.
So it bounces back into.
It bounces, and it's going to be bouncing back and forth between 1 and negative 1 forever. Again, this isn't calculus, so if this were a calculus class, I'd say, what does this converge to, or does it converge? The answer would be it doesn't converge, because all of these are negative, and they're all getting closer to 1. All of these are positive. They're also getting closer to 1, and so this one's approaching positive 1. This one's approaching negative 1. Yeah, and that's so tricky. But again, that's not our point for this class. I'm not too concerned about that. Okay. Everybody got this?
Yeah.
This is going to be homework stuff. It's going to be like this. What are we doing? I need to write a little bit. Okay. Here's another one. Same question. Find the first 4 terms and graph it. What's the first term?
5.
What's the second term?
5.
It's just 5, right? It's 5 forever. Okay.
Just a
This is
line.
the same kind of thing when you have, like, this is basically
But there's
this.
the
F of
point.
x equals
Wait.
2, right? It's always 2,
Yeah.
right? This is just saying a of n is always 5, no matter what value of n. You plug in a 1, you get out a 5. You plug in a 2, you get out a 5. This is, I'll make it exactly the same. This says you plug in a 1, you get out a 5. You plug in a 2, you get out a 5. That's what's going on there. Okay, but it is an infinite sequence, so there's infinitely many 5s. And if we wanted to graph it, 5, 5. It is not a straight line, right? Because this is an infinite sequence. It's only defined on 1, 2, 3, 4, and so on. So it's infinitely many points at 5. Everybody got that? By the way, I'm sorry, that's right there. That should not be there. Right? That was an aside. This is that. Okay. All right. Okay. Okay. Everybody got this? Pretty simple stuff. You plug in stuff into a formula. Pretty simple. Until we get to this right here. Now, these are what's called recursively defined sequences. They are recursively defined. This will become clear soon. I give you the first one. And your book is only going to do where they give you the first one. I'm going to do one where I give you the first 2. And then I give you a formula for how you could find the next one based on the previous ones. So this one is going to be that one plus that one.
Oh, so it's the Fibonacci.
It is the Fibonacci sequence, because why? Let's just do it. A1 is equal to 1. A2, it tells us is equal to 1. A3, now we have to look at our definition, and if n is equal to 3, then n minus 1 would be 2. So it's the same thing as A2 plus A1. Everybody got that? Right? That's 3. That n is 3. You take 1 off of it, you get 2. You take 2 off of it, you get 1. Well, that was 1 plus 1, which is 2. And so then A4 was the sum of the previous 2, which would be A3 plus A2. Right? Just check that. If n is equal to 4, then n minus 1 is 3, n minus 2 is 2, A3 was 2, A2 was 1, and we get 3. And so on and so forth. Right? And so this is what we call recursively defined, because this is recursive. It's recursion. This right here, where you take something and then you're going to put it back in, because like we saw, that's how we got 3, but then 3 goes back into the definition of the thing itself, right? That's what recursion is. That's another way you could define a sequence. And so, our book always starts with n equals 1. Yes, I already talked about that. Okay. Again, some authors do it differently. Okay, so that's a recursively defined sequence. So here's number 22. Find the first. We're only going to do 3. No, I said 4 terms. I think your book says find the first 5. But here's one. A1, the first term is 5. K plus 1 is equal to 7 minus 2AK. So in other words, whatever your previous one was, you put it in here, and that's how you get the next one. So in order to get A2, we have the 7 minus 2 times A, the previous one, right? That's the previous one, so that would be 1, which is 7 minus 2 times the previous one was 5. This works out to minus 3. Okay, we're finding the first 4 terms. We're almost there. This would be 7 minus 2 times A sub what? 2. 2. Because if that is 3, then that is 1 less than that.
Yeah.
So that has to be 2. And so that's 7 minus 2 times negative 3 works out to 22. I could be wrong about that. I don't know. 4 would be 7 minus 2 times a to the what? Or a what? 3. So that's 7 minus 2 times 22, which I could be definitely wrong with this. Look at that, 37, that's, yikes. But yeah, that's the idea, right? You just plug in stuff back in. And this is then the sequence that you get. You define a sequence that way, and then it would be 5 minus 3, 22 minus 37, and so on and so forth that way.
So these ones don't like what?
Converge.
Yeah, converge.
It looks like that one's not converging. It really does. And if you think about what this formula says, if you think about this as a y equals 7 minus 2x, that's a line. Does something like that. It's looking like the bigger this gets, that also gets bigger, right? The outputs are going to get bigger. But it's going to blink back and forth between positive and negative, but it should continue to get, as you go further that way and that way, that's getting bigger and bigger in the y direction, so it looks like it's not going to converge. Again, we are not concerned with convergence in this class. But that's how you would figure something like that out. Here's one that probably will converge. I kept saying, like, as I was going, like, writing this stuff out, I was like, don't talk about convergence. Don't talk about convergence. But it is, like, if you go on in math, that's all you're going to talk about for like a year and a half is, does this converge? Does this converge? Does this converge? And it's, yeah. Anyway, okay. 128. The first term is 128, and we define the next term by saying it's 1/4 whatever the previous term was. So A2 is 1/4 times what?
128.
Which is?
128 over.
I think it's 32.
Yeah.
Yeah, that's what I got. Because 128 is a power of 2, 4 is a power of 2. It's actually not bad. And so then, okay, A3 is what?
1/4 of.
So, 4.
Wait, no, 8. No, 8.
I think 8. A4 is?
1/4 of 8, which is 2.
That was the fifth one.
1/4 of 2, which is 1/2.
And so on. Now here's the thing. This one's actually, it looks like it's converging. Looks like it's
To 0.
It looks like it's converging to 0. And here's just something to notice. Is like, okay, we got that by doing that, but how did we get this? Well, we said this is the same thing as 1/4 times the previous one. But what was the previous one? Well, it was 1/4 times the first thing, which was A1. So that's 1/4 times 1/4 times A1, which is 1/4 squared times A1.
Because you could write it different.
And how did we get this guy? Well, we said it was 1/4 times the previous thing, but what did we just say the previous thing was? That right there, which is 1/4 times 1/4 times A1, which is 1/4 to the third A1. This, how did we get that? Well, it was 1/4 times all of this previous stuff, which was 1/4 to the third,
1/4 to the n minus.
1/4 to the 4A1. And so let's find the nth term.
1/4 to the n minus.
Is it n?
To the n minus.
Yeah, there you go. Because like that's what we have to look for, right? It's like, well, when it was 5, the exponent was 4. When it was 4, the exponent was 3. When it was 3, the exponent was 2. So it's always 1 less, and so when it's n, the exponent is n minus 1. Yeah. There you go. Nice, nifty formula right there. And if we'd started with any other number, that's why I didn't choose to write it as 128. Like, it's, you know, it's nice and general this way. You can just plug in any initial value, blah, 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 blah. Okay. One last thing to talk about, and we do have time to talk about. Does this make sense? I don't think your book ever asks you to find a general formula for this stuff, but as we go on, it will be very useful if you could do this kind of thing and go, wait a minute, this is happening. Can I come up with a formula? And if you can come up with a formula for the nth term, your life is going to be so... Like, for years, what you're going to be doing is asking yourself the question, can I come up with a formula for the nth term in a sequence? Sometimes you can, sometimes you can't, but when you can, your life just gets so much easier. Okay, here's a question. What's the next term in this sequence?
3.
It's not.
How do we?
Okay, well, here, let me give you the next term and see if you can tell me what the next term is. It actually goes 1, 2, 6. So what's the next term?
Wait.
Not. No, 10.
12. No.
Oh.
18.
You say 9, you said 12, and I heard 9, 12, and 18. It's actually not, it's actually 24. Can you tell me what the next term of the sequence
1,
is?
2, 6, 24.
It would be
Oh.
so-
Is it? Wait. Is
Ooh.
it 20? Is this something times 5?
Yes, it is. Yes, it is. That's really, really good. It is something times 5.
Is it
It's
24 times 5?
Yes, it is. Now, okay, so you were able to figure out
Oh, I see.
the one that I was. Yeah. So what we did is we started with one. What did we do? Well, this is what we did. A1 was 1, and then what I said is the way you get the next one is you take the previous one and multiply it by whatever. Oh, yeah. Then you multiply it by whatever number you're in.
Yeah.
Right? And so, now here's the thing. My point with this is just given a few terms of a sequence, you cannot tell what sequence it is. Like if I said 1, 2, what's the next one? Well, it could be 3, it could be 6, it could be 8, it could be 4, right? Like it might be, well, you take 1 and then the next time you multiply that by 2. And then you multiply that by 2 to give you 2 squared. And then you multiply that by 2 to give you 2 to the third. But the point here is that given any number of terms of a sequence, you cannot tell what it actually is. There are other types of sequences. There's things called arithmetic sequences. There are things called geometric sequences. Geometric sequence is something that's multiplied by a constant term every time, something like this. Arithmetic sequence is that the difference between these guys is the same every time. And then there are a bunch of other types of sequences that don't have nice nifty names and blah blah blah. This is one that has no nice nifty name. But yeah, it would go 120. And then I think it's like 720? I'm not sure. But whatever. This is actually a very important sequence that you're going to see a ton. And we'll talk about it at length. Actually, later this chapter.
Does it
Yeah.
have a name?
Not as a sequence, but as a function. It has a name. And it is very, 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 very useful. My whole point with all of this was that, oh, and just to be clear, what I was saying here is like, yes, we started with A1 was 1. Then A2 was 2 times A1, which was 2. Then A3 was 3 times A2, which was 3 times 2 times 1. And then A4 was 4 times A3, the previous one, which is 4 times 3 times 2 times 1. Then A5 would be, you guessed it, 5 times 4 times 3 times 2 times 1, and so on and so forth. And that's how I got those, but you can't tell that that's what I was doing even by that much. And Victor, I am so proud of you that you got that one and said, I think what you're doing is this, and you happen to be right. The point is, you cannot, unless you're given more information, unless it's either defined by a formula, which in case, actually what this thing is called is factorial. This is n factorial. It's not n, it's n factorial. And that's what this means. So if you have 5 factorial, that means 5 times 4 times 3 times 2 times 1. And 72 factorial would be 72 times 71 times 70 times 69 times, and so on, all the way down to times 2 times 1. That is, we're going to see it.
Big number.
It's ridiculously huge. It's really, really, really huge. Nothing, well, there are things that grow faster than factorial, but factorial grows faster than any exponent. Even the exponent like 100 to the x is much, 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 much less than factorial, x factorial, eventually.
What about infinity?
There is not a number. It's not a number. Do push-ups. No. So yeah, that's the idea. And so my whole point is that unless you're told this is a geometric sequence, This is an arithmetic sequence, which we'll talk about briefly in this chapter. But unless you're told something like that and you're given any number of numbers, you cannot tell what's next in the sequence. But they has to be given either by a formula or defined recursively, and that's the idea. So you guys got homework, and then we're going to go into the next thing we're about to do in this chapter. It's going to be so ridiculously helpful for calculus and everything you do after that we're going to really, 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 really want to pay attention.